And hello, and welcome back to OneClass. Again, my name is Joey. I'm going to be your chemistry teacher for this session. So just a little bit about us. Again, here at OneClass, what we're doing is that we're providing and we're verifying solutions that you would typically have in a chemistry level, a chemistry or mathematics secondary school level, but also in the college and the university level as well. So basically verifying solutions from frequently asked questions from students all around the world. And we have basically compiled a list of questions that OneClass believes that it's the kind of best questions to answer. What we're doing here is we are verifying these solutions so that you have the best solutions moving forward. So my name is Joey. I'm currently a secondary school educator in the Ontario Board. My teachable subjects are chemistry and music. However, I'm planning to get my teachable in math as well. So I have about 10 or 11 questions for today. It's going to range from basically anywhere from grade 11. There's like one question grade 10 all the way up to organic chemistry. So that's how we're going to kind of split the session for today. And yeah, let's get started. So what we have here is the first question is asking us, what is the molar mass of silver nitrate? So let me write this down here for you. So number one, give me a second. So let's see here. My pen's not working, sorry about this. Might have to. There we go. Let's see if this works. There we go. Okay. So let's see, it's talking about the molar mass of silver nitrate. Yeah, I might have to refresh this. There we go. Okay. So I want the molar mass of silver nitrate. So typical question about molar mass and of kind of like a little stoichiometry here, but we don't really need to convert anything from mass to moles here, or in between that, we just have to find the molar mass of silver nitrate. So in order for us to find the molar mass of silver nitrate, what we're gonna have to do is write down the chemical formula first. So again, silver nitrate, I'm gonna have two compounds here. One is silver, so silver is AAG, so you probably know. And nitrate here, nitrate you can't really find on the periodic table. It's more so a polyatomic ion. So when we talk about polyatomic ions, they're basically ions that they're basically kind of non-metals that are bonded together, covalently bonded together that have a charge here. So a nitrate here has a charge of, it's basically NO3, NO3 minus, and Ag is has a positive one charge. So if you can think of this as you can do the crisscross method, or you could do kind of logic in the sense that, oh, I need one positive or one silver atom here to satisfy this negative charge, because 1 plus negative 1 here equals 0, and I always want a charge of 0, right? So therefore, my chemical formula for silver nitrate is AgNO3. Now, once we have AgNO3 as our chemical formula, what we can do is we can find the molar mass, right? So I'm going to have to bring up a periodic table. So just give me a second here. Let me find a periodic table for you. And what we're going to do is we can calculate the molar mass of silver nitrate. So in silver nitrate, as you can see, how many atoms do we have of each element? So let's count. So we have Ag, we have one silver atom here, right? We have one silver atom. We have one nitrogen atom, so 1N here. And we have O3, which means we have 3 oxygens as well. So I'm going to put equal sign here. So all these guys here, what we're going to do is we're going to add up all the molar masses together to find the total molar mass. So silver, if I go into my periodic table here, I'm looking for silver here. Silver here is number 47, right? It's a transition metal. It has a molar mass of 107.87, or atomic mass of 100.787. We're going to assume 1 mole of the substance here. So it's going to be 107.87. So I can write here 1 times 107.87 grams per mole. I have nitrogen here, so it's 1 times, and then I'm going to look at the nitrogen. Nitrogen here is a non-metal, so I'm going to look at the right on my periodic table here. As you can see, N here is number 7, and my atomic mass here is 14.007, which means my molar mass is also 14.007 grams per mole. And finally, I have 3 times oxygen here. If I look at oxygen, oxygen is right beside nitrogen here. Right? O here is 15.999. So go back. 15.999 grams per mole. And then we shift this slightly to the right here. And what we can do now is we can multiply in, right? So we have 1 times 107.87 is simply just 107.87 grams per mole. We have 1 times 14.007, so it's simply just 14.007 grams per mole. And finally, we have 15.99 times 3 here. So let me just use my calculator. 15.999 times 3 would get me 47, sorry. 47.997 grams per mole. What we can now do is we can sum all of these up. So we add the molar mass of silver, molar mass of nitrogen, and the molar mass of oxygen here. So we have 107.87 plus 14.007 plus 47.997, and that will give us the total molar mass of silver nitrate. So this here is our answer. 167.874 is our answer for the molar mass of silver nitrate. So as you can see, they did the exact same thing here. So they wrote down the silver the chemical formula, which is silver nitrate, which is AgNO3, and what they did was they counted the atoms together, right? So you have one atom of silver, one atom of one atom of nitrogen, and 3 atoms of oxygen. And then what you do is you can just simply multiply it, right? 1 times 107.87, 1 times 14, and 3 times 16 here. So very, very approximate here, very, very close. They get a total of 169.86. I got 169.87, so this solution here is correct. Good analysis here. All right, so this is an organic chemistry question. Number 2. It's asking us, predict the major product for the following reaction, fuming H2SO4. I keep getting it wrong. Test bank question 072, your answer is incorrect. Okay, so it's just basically predict, right? So basically I care about this guy here. So I have his benzene. There we go. So this is basically reactions of aromatic compounds, right? So I have a benzene here. Whoops, it's not that pretty. That wasn't pretty either. There we go. So benzene here, I have an OCH3 group, so some ether group. I have CCl3, and then I have this here H3CO. H3CO. It's bonded to the O actually. So let me rewrite this here. H3CO. Okay. Let me move this number 2 here. Okay. Yeah. So I have this question here. It's asking us if I react this with fuming H2SO4. What do I get? So what this person wrote here is that they actually wrote that. So I have again 2 ether groups here. I have CCl3 here, and so they said it was going to react kind of ortho to this ether group here, which is wrong. So and they said they got the question wrong, and why is this wrong? So if you think about this question here. We think about this question using kind of electron withdrawing and electron donating groups, right? We have CCl3 here. We have some sort of dipole moment, right? So this CCl3 is pulling electron density away from this benzene because it's a negatively charged halogen here. So it's pulling electron density away. Same with this oxygen and this oxygen as well. However, because there's 3 chlorines here, it's going to pull electron density much further away, right? So when we react it with if you make H2SO4, it's actually not going to go ortho to these guys here. It was not going to go to this position here, or this position here. It's not going to react to any of these positions. It's going to actually react with this position here. It's going to be para, or sorry, it's going to be ortho, not ortho, sorry. It's going to be para to this CCl3. Sorry, I said ortho. This is para, sorry. So it's going to be para to CCl3, and not para to H3CO and OCH3 here. So let's see, what do they write here? These answers writing, okay, OMe, that's good. So again, it's electron directing group and the meta electronic group, which is good. So ortho to 1 and meta to CCl3, H2SO4. So this is the electrophile. So they have here, they actually have here, they wrote that this is going to go para to H3CO here. So let's see, give me a second here. I'm just going to read their solution. So they said ortho to OMe and meta to CCO3. Yes. So it's ortho to, so basically, okay, so this solution here is correct. So I kind of messed up here, and I said that I mixed it up. So I mixed up that ortho here. It's going to be ortho to OMe, so ortho to one of these, but it's also going to be meta to CCl3 here. And the reason why we have that is because we have, again, 2 electron directing groups and with 3 technically electron directing groups. We have 2 unique ones. So we have one CCl3 and one that's a OHC3. And we know that this one here is a meta directing group, right? This one's meta, and OCH3 here is ortho and para. Para meaning that it is very much opposite. So para would have been, para to OCH3 here would be this point. Para to OCH3 would be this point as well. But it can also add para, right? It can also add, it can also add ortho. Ortho is simply just this point here and this point here. It's right beside the OCH group. But we also have to consider CCl3. When we consider CCl3 here, we're thinking of this meta position, right? Meta to CCl3 would be this position here. So if I want to satisfy both CCl3 and OHCH3 requirements, I'm going to have to do meta here. So meta, it has to be meta here. So it can be either this position or this position, but it has to be ortho, or as we do ortho to this position here, which means the only position that's correct would be this position here. So it's going to sulfonate at this position here. So this answer is correct. Sorry, I mixed it up when I said ortho and para. Remember, when we're talking about meta, ortho, and para, we're talking about the locations of the benzene substituents, right? So we're talking about the ortho, para, meta directors, right? So when we think about meta here, meta is 2 away from the electron directing group here. And then when we think about meta or ortho here, we're thinking about right beside it, right? Right beside it. And para is right opposite of it. The furthest away it would be para. So let me write this down for you. So this would be closest. And this would be second closest. And this would be the opposite, right? Opposite away. So if I want, again, I'm fulfilling meta here, which is the second closest here, which is this point, and I'm fulfilling ortho here, which is this point or this point here. So this solution here is correct, and basically it's going to sulfonate at this point here. So I'm going to redraw the benzene. I have CCl3. I have CH3CO, OCH3. And then finally, it's going to sulfonate at this point. So I'm going to SO3H here. So this solution here is correct. So it's going to, basically, we know that sulfonating is a protecting group. So it's going to protect this point over here. So the solution is correct. They actually had it on the opposite side, but yes, the solution here is correct. Yeah, so we'll move on to number 3 here. So let's do number 3. All right. So it says determine delta G for the following reaction. This is number 3 here. And use delta G F from the Gibbs energy formation from a data of it from a table. Okay. So number 3. So I have this chemical formula here. C3H8 plus 5O2 yields 3CO2 plus 4H2O. I'm just not going to include the phases, but I know this is here is a combustion reaction, right? This here is a 5, not an S here. There we go. I know that the delta G, not a formation of C3H8 would be negative 23 kilojoules per mole. I know that delta G formation of CO2 would be negative 394 kilojoules per mole. And then finally, delta G formation of H2O would be negative 237 kilojoules per mole here. So that's gets determined for the following reaction. What are we determining? So to determine the delta G for the following reaction here. So let's do this problem. And we're going to say that we know that delta G naught of this reaction here, you could think of this problem as kind of like Hess's law, right? Where Hess's law states that the enthalpy change of the reaction is simply the delta energy change between the products minus the delta energy change, enthalpy change for the reactants, right? So I can basically say that delta G here for the reaction will also be basically delta G, or Gibbs free energy, of our products minus delta G of our reactant. So it's very, very similar to Hess's law, but it's kind of rearranged, right? It's rearranged for delta G, for Gibbs free energy. And we know that we can actually relate this to Hess's law, because I know that delta G is simply just the enthalpy change. I can do delta H here minus temperature times delta S, right? Where delta S here is the entropy. So this formula here allows me to relate delta H with delta G, and that's why we can use this reaction here, because it's very, very similar to Hess's law. But we know that if we have a change, if our temperature here is consistent, and we make our entropy here constant, then we can basically state that delta G here equals delta H here, right? So we can basically use this this formula here to solve for our problem here. Let me keep this actually. I'll keep this for reference. I don't know why I erased it. Okay, so I'm going to let you think about this problem for just a couple seconds. So think about delta G for products, delta G for reactants here. What are my products, what are my reactants in terms of our chemical equation, and how will we solve for this problem here? So I'm just going to turn on light because it's just a little bit dark in my room. So I'm just going to leave you this question for a couple of seconds here. So what we have here is, again, we want to know, we're determining the delta Gibbs free energy of our reaction here. So we have basically delta G of the products minus delta G of the reactants, right? So I forgot the subscripts here, which is formation here. Let me write this down here. Delta G formation here. And basically I know my products here. My products here are carbon dioxide and water, right? So I can say basically our products here are carbon dioxide, which is this guy here, number 2, and number 3 here, water, right? So let me just write down number 2 and 3 here. So very, very similar to Hess's law, where instead of enthalpy, we're just using Gibbs free energy here. So this is going to equal products here, which is 3 carbon dioxides, right? Again, I'm forming 3 carbon dioxides, so I have to use this Gibbs free energy 3 times, right? Coefficients do matter here, so we have to make sure that we know that this here is already a balanced chemical equation, so we don't have to worry about the coefficients being incorrect. So we can write here 3. I'm going to multiply it by the Gibbs free energy of carbon dioxide. So this is 394 kilojoules per mole. Plus, remember, it's a sum of this is a sum of our products, right? So you can basically say this here is a sum, and this here would also be the sum, actually. So maybe I'll write the summation here. Plus, so this is all kind of in brackets here, plus the water, right? I'm also making water as our products here, right? So I have 4 waters here, which means I'm making 4 times negative 237, right? 4 times negative 237 kilojoules per mole. So basically that's all of that here, plus, or minus, sorry. So I'm going to minus my delta GF of my reactants, right? In this case, my reactants here, I have this is my propane, and this here is my oxygen gas, right? So propane would have a delta GF of negative 23 kilojoules per mole, right? So we have here, and that's only simply just a 1, right? So we have basically 1 times, this would be negative 23 kilojoules per mole. And then for oxygen gas, because I know here it's a diatomic molecule here for oxygen gas, oxygen already exists as O2. Remember, it's a diatomic molecule. You can think back to Hofmannsthal, the mnemonic here. We know that this here, because it's just simply just an element that exists as 2, it does not have a delta G of formation, and it's actually 0 in this case here. So we can say that so we can just simplify this this equation here and say that we can say that our formula here is we can actually get rid of the oxygen here, so we don't even have to write the oxygen here. You could say plus also 0, but it doesn't really matter. Adding 0 to the equation doesn't do anything. So to get my calculator, I'm doing 3 times negative 394. Gives me negative 1,182 kilojoules per mole, plus whatever 4 times negative 237 is, which is negative 238, or sorry, negative 948. So I'm going to add both of these guys up, and then I'm going to minus that by minus 23 kilojoules per mole. And then I'm going to add, again, it's just simply just algebra right now, right? I'm going to add both of these guys up first. So negative 1,182 plus negative 948 would give me negative 2,130 kilojoules per mole. And I'm going to subtract that by 223 kilojoules per mole to get my final answer, which is negative, it's minus, so this here is plus, sorry. So this here would be negative 2,107 kilojoules per mole. And this here would be the delta G naught of my reaction here of reaction. So this solution here is correct. Again, they wrote here, they wrote kind of the same thing as I did. They basically just wrote out Hess's law, and then they looked at the products and the reactants, and then they just simplified here. So the solution here is correct. We can, and then I'm going to say we can relate Gibbs free energy with Hess's law because delta G equals delta H minus T delta S. Therefore, Hess's law can be rewritten as a function of Gibbs free energy. Solution here is correct. Okay, next question is question, I believe it's 4 here. So it's asking us how many valence electrons are in the silicon atom? So how many valence electrons are in silicon? So there's a couple ways to think about this problem, depending on when it's asked. In terms of, if this was asked in terms of a lower level kind of chemistry or science course, you would basically draw a Bohr Rutherford and you would think about how many valence electrons exist in the shell. So let me just do that one first. So you can think of this problem in 2 ways. So you can think of this problem as let's see here. Let me just see here. 1 and then 2 and 3 here. So you can think about Si being in the middle. So Si here is in the middle. You can have 1, 2 2 electrons in the first shell, and then it signifies that it's in the first column here. The second column is all filled as well. So you can say that I have 8 electrons in my next shell, not valence, sorry, 8 electrons. And then finally in my last shell here, I have 1, 2, 3, 4, right? I have 4 electrons here. So give me 1, 2, 3, and 4 here. So this here you can say, oh, because I have 4 valence electrons here, in the last shell I have 4 valence electrons. So if it was asked in terms of a lower level chemistry question, you can say that silicon here has 4 valence electrons, just because you see here, I'll highlight this in blue, there's 4 valence electrons, there's 4 electrons here in the outer shell, right? So if it was asked in that context, this solution would be correct. However, if it was asked in terms of a grade 12 context or a senior level chemistry question, then you have to write out the electron configuration of silicon and see what valence electrons are available, right? So if it was asked in it, so this is a grade 9 question here. But if we want the electron configuration, of silicon, what I would have to do is I have to write Si here, and then I have Si colon here. So I'm writing my square brackets here. So again, silicon here, I have 2 electrons in the first energy level, so it's gonna be 1s2. I have in the secondary energy level, 2s2 is also filled, right? So 2s2 is filled as well. 2p6 is also filled, right? All of these electrons are filled here. So 2p6 is filled. 3s2 is also filled, right? This is 3s2 here. So 3s2 is filled. And then finally, I have 3p and then 2, right? I have 1 and then 2, and I'm at silicon here. So this is 3p2. And basically, if I want to look at the valence electrons here, I'm looking at my electron configuration here. I'm looking at the last orbital, or the last energy level, which is at n equals 3, right? So at n equals 3, this here is my principal quantum number here. I'm going to look at these 3 here, these guys too. And as you can see, I have 2 s orbitals, or 2 s electrons. 2 electrons here on 3s2, and 2 on 2p on 3p, right? So I have 2 3s electrons plus 2 3p electrons. So therefore, I have 4 valence electrons. So it really depends on how you think about this problem here. Again, in reality here, we know actually silicon hybridizes, and we actually know that this it doesn't actually have it forms 4 bonds by doing by splitting this to 3p 3 sp3 orbitals, right? So basically, these 2 energy levels actually hybridize to form 3 sp3 orbitals, but you for basically the extent of the question, you won't need to know this kind of concept here. So basically, it has 4 valence electrons. So 1, 2, 3, 4. As you can see by the Bohr-Rutherford diagram, and as you can see by the electron configuration here, this says highest principal energy, or the principal quantum number here is 3. So therefore, I'm adding 2 plus 2 here is equal to 4. So solution here is correct. Okay, number 5 says draw the neutral organic starting material. So basically, I have something. It's going to react with Br2. So again, organic chemistry level question, and also CH2Cl2, and it's going to create some sort of epoxide, or not an epoxide, sorry, more so a heterocyclic structure with a bromine here. So I have so basically it's asking us what is our neutral organic starting material if I'm given this final material here, and I have these reagents, right? I have Br2 and CH2Cl2. So let's look at the answer here, and it's saying here that you need here this guy to make this, right? So what does that mean? So we can think of this problem as, you can look at this problem by counting the carbons first, right? So let's count the carbons here. So again, we have one carbon here, 2, 3, 4. This isn't a carbon here, and then 5, right? So minimum, I'm going to have a 5 carbon chain to start with, right? So let me write this down. So we're going to have a 5 carbon chain. So I have 1, 2, 3, 4, 5, right? So 1, 2, 3, 4, 5. 1, 2, 3. So I'm going 1, 2, 3, 4, 5, right? That's good. So I'm going to have a 5 carbon chain here. I know that one of these ends here has to have an oxygen, right? And if I were to, again, break up this heterocyclic atom here with the oxygen, I'm going to get an OH group, right? So I can safely say that this bond here has to have a hydroxyl group, right? So this here would have to have my hydroxyl group here. And then finally, if I want a Br here, if I want a bromine here, what would I have to get in my starting material to get a bromine? Well, I would need either an alkene, so what they have here, or you could do some type of substitution with an iodine group. So it doesn't really matter which one you put here. You could put an iodine, or you could put a bromine, but in this case here, they put an alkene here. So that Br2 can add to the 5th carbon here. And I'm just gonna check if this is if it actually goes anti-Markovnikov here. It should add specifically to it should add basically to one of these guys here. So it should, in this case, Br2, it's going to, again, CH2Cl2. This is going to fold into the oxygen here to create this 4-membered ring. So again, I'm going to count my carbons again here to show you. So I have 1, 2, 3, and 4. And then it's going to, basically, this guy is going to fold into the oxygen here, so create this ring here, and then the 5th carbon is going to be then attacked by the bromine here. So basically what happens is that these electrons like this bromine here. So basically I can draw an arrow. Let me break up this Br2 here. So basically draw an arrow from here to here. It's going to kick out one of these bromines. It's going to form an intermediate that has a positive charge, right? So I'm going to get something like so. And then what it's going to do, it's attracted to this oxygen. So it's actually going to fold into here. And then this bromine, the Br minus, is now attracted to this oxygen, to this positive charge here, right? So this here is going to fold in first to make the ring, and then this Br minus is going to attach to the 5th carbon here. So this is how, so that's how it forms kind of this guy here. So the solution here is correct. It's a great analysis as well. I just didn't really write analysis, so I'm just going to say solution here is correct. That's about it. Okay, number 5. Number 6 is asking a solution containing 2.0 times 10 to the negative 4 silver, the silver cation Ag plus, and 1.5 times 10 to the negative 3 molars of lead 2 plus. If sodium iodide is added, will silver iodide or lead iodide precipitate first? Specify the concentration of I minus to begin precipitation. Okay, so I've given a lot of things here. So let me, number 6. Give me a lot of information here. So let me write this down here. So I'm going to have, I have 2.0 times 10 to the negative 4 moles of Ag plus. I also have 1.5 times 10 to the negative 3 moles of Pb2 plus here. And as if sodium iodide is added, will silver iodide or lead iodide precipitate first? So I'm adding sodium iodide, right, to this kind of equation here. So what I can do is, again, I can write the chemical equations down, and I'll write sodium iodide, or actually I'll write Ag plus here. This will be 2 chemical reactions. So this is 1, 2 here, right? So 1 here would be Ag plus sodium iodide, which will give me, and this could be in equilibrium, very much so. So this would be it's going to replace it, and it will go. This would be AgI plus Na plus, and then number 2, you would have Pb2 plus sodium iodide react to form sodium or lead iodide and Na plus here. So again, we have our 2 reactions here, and then we know here we have a solution here, and we have our KSPs here, right? So the KSP for these guys here are, let me write this down, KSP for sodium iodide would be 8.3 times 10 to the negative 17, and then the KSP for lead iodide is 7.9 times 10 to the negative 9. So asking which one will precipitate first, right? So let's look at, let me zoom out and look at this problem here. And so let's look at the first guy here. So first guy here, I can basically write a KSP kind of I can write our KSP equation. Sorry, that's the word I'm trying to say, equation here. And so I can write that KSP here. You write KSP here equals, it's going to equal our basically our sodium our silver iodide here. So our silver, or sorry, not silver iodide, silver times our iodide here, and KSP for this guy here would be our Pb2 plus and I2 minus, right? So we have these KSP values here. And what we can do is we can get, we can create some type of equation for us to solve for our the concentration of iodine, right? So that's kind of what we're doing here. So KSP is going to equal our Ag plus times our I minus, and then our KSP will be Pb2 plus I minus, and this will be to the power of 2 because I need 2 iodines here. I need 2 iodines. So you can think of this as I need 2 iodines here because I have to balance my chemical equation, right? So this here is my KSP values for both 1 and 2. Now what I can do here is I can substitute my concentrations here to solve, right? So let me do that for you. Again, I have 2.0 times 10 to the negative 4 molars times I minus. This would also equal 1.5 times 10 to the negative 3 molars times I minus to the power of 2. And I believe they did the exact same thing here. And they plugged those problems in. And remember, we know that our KSP values here are 8.3 times 10 to the negative 17 and 7.9 times 10 to the negative 9 for these guys here. So let me rewrite this now. Maybe I'll do blue for Ag iodide here. So KSP for 1. So this for 1. Is going to be 8.3 times 10 to the negative 17. It's going to equal 2.0 times 10 to the negative 4 moles times I minus. I can simply divide both sides here to get my I minus concentration of I minus, right? So I'm going to write down 8.3 times 10 to the negative 17 divided by 2 times 10 to the negative 4. This will equal 4.5 times 10 to the negative 13 here, which is exactly the same thing as what they got here, which is great. This is our concentration of I minus here. It's going to be 4.5, sorry, times 10 to the negative 13. Oh, that's 15, sorry. Moles. And then for number 2, and my KSP of lead iodide, which is 7.9 times 10 to the negative 9. This will equal our concentration of lead, which is 1.5 times 10 to the negative 3 times I minus to the power of 2, right? So again, I would divide both sides by 1.5 times 10 to the negative 3, and I would get 7.9 times 10 to the negative 9 divided by 1.5 times 10 to the negative 3. I would get 5.266 or 7 times 10 to the negative 6 equals I minus squared. You could square root both sides to get I minus alone, right? So I minus here would be 2.29 times 10 to the negative 3 molarity here. So as you can see, this here is, so I have the concentration for iodine for my silver iodide and the concentration for iodine for my lead iodide here. So clearly we need much less for our silver iodide, right? We need a lot less, right? So again, so it says which one will precipitate first? Well, as I add, depending on how much I add in terms of iodine, well, I know that silver is going to precipitate first, right? So in this case here, I need a lot less for me to precipitate my silver. So therefore, silver here is the correct answer here. So so again, which one will precipitate first? Well, silver iodide will precipitate first, sorry, and I'm only going to need 4.5 times 10 to the negative 3. So again, this solution here is correct. Good analysis here. Let's see if we can do maybe 2 more questions depending on time here. So that's number 6. Number 7 says draw the major organic product for the following reaction. So I have 1, 2, 3, 4, 5 Cl. I have H2O and isopropyl alcohol. So something like that. And then I basically, I have 2 questions here, right? Oh, I have 3 actually, or 4. I have 4 questions here. I have a lot of questions here. So let me just, I'll have to analyze this as quite a bit of, maybe I'll do these 2 first. And then for the sake of time, I'll skip down to the solution and just explain it to you because, it's going to take a lot longer for us to kind of figure this out here. So it's NaCl and H2O, and then I get some sort of product here. Okay, so let me see what the solution. Let me see what they have solution here. This looks like a very awkward diagram, but let's look at the solution here, and we'll see if this is correct here. So they have here, I'm reacting this kind of alkyl group with a chlorine. I'm going to react it with with H2O and isopropyl alcohol. And then I'm going to get this guy here. So let me think about this problem here. So this chlorine group, what it's going to do is first it's going to, again, leave, right? So this chlorine group, I mean, if I'm going to draw out the mechanism here, if I'm adding water to it first. So water here, as again, this here is a negative charge here. This here is also partial negative, which means this here is partial positive. So again, this guy here is going to come and then kick this guy out, right? Or it can wait for it to leave first. So I think it's going to wait for it to leave. Actually, I think it might be an SM1 kind of type of reaction here. So I think the first step is this chlorine's going to leave here. So I'm going to get, something like this. I'm going to get a positive charge like so. And what it's going to do, it's going to do something called a hydride shift, right? So if a hydride shifts here, I have one hydrogen here. It's going to come and swap places, right? Swap places with this carbocation. Because currently here I have a secondary carbocation, but I can hydride shift it to make it a tertiary carbocation, right? This here is a secondary carbocation, and I want to make it a tertiary because it's more stable. Element and compounds like to be more stable here. So I get something like so. So this here would have I would move my hydrogen here. My hydrogen is now here. So it's going to hydride shift it. So my carbocation is now here. And now what I can do is it's going to now react with my water and isopropyl alcohol. So water here and isopropyl alcohol. So again, what it's going to do is, again, it's going to come and this minus here is basically come and attack kind of this this point here. It's very very attracted to this, right? So let me I think I wrote red here as positive. So this here is the lone pairs of hydrogen is going to come here, and then it's going to make, again, this compound here. It's going to make this compound. So I have 5 here, 1 here, O, and then something like this here. So this here is a correct solution for number 1 here. Again, water could have actually done this this deprotonation here as well. So you can think of water here helping this chlorine group leave. But chlorine here is it's a decent leaving group. It depends if this oxygen here comes and decides to attack here and then leaves it out. And you would get this intermediate first, and then you would hydride shift it so that you would get a more stable carbocation, so you can get this compound here. Okay, number 2 is now asking us, we have this compound here, and then if I react it with sodium chloride and water, what would I get here? So in this case, I can't make a tertiary carbocation, right? So this here is another trick question. It's trick question of the first one here. I'll show you why. So I have 1, 2, 3, 4, 5, 6, and then a Br here, right? So again, you think of this problem as, okay, I have NaCl here. So again, obviously, my bromine here is partial negative. I think I did negative with the blue, right? Yeah. This bromine here is negative, which means this guy here is partial positive. And then I have sodium chloride here, which is Na plus and Cl minus, right? So Cl minus is going to be very, very attracted to this dipole moment here. Come and kick out the bromine here, right? So I'm going to get here now this bond Br, or sorry, bond Cl plus NaBr, right? And again, this reaction works because chlorine is more electronegative than bromine, right? You can look at this periodic table here. Chlorine's above bromine here, so that's why it's more electronegative. So it's going to kick this guy out. If it was the opposite, if it was NaBr and chlorine was already bonded to this, the reaction wouldn't happen here because chlorine is more is more tightly bonded to this carbon here than chlorine. Or sorry, chlorine is more bonded or more attracted to the carbon as opposed to bromine here. Okay, so now we have this compound here, and then finally what we're going to do is if the lone pairs, so we on oxygen, so let me again write out my dipole moments again. So again, I have partial positive here, I have a negatively charged chlorine, also have the lone pairs on oxygen, right? Lone pairs on oxygen are going to come here and kick this chlorine out. So you get something like this. And again, you would get first a carbocation, or get this guy here, right? Or I'm writing the intermediates for you as well, so you can see what will happen here. So I have again secondary carbocation that's being created before another nucleophilic attack, right? So in this case, remember in our last case here, we had a hydride shift. This hydrogen from this guy here is going to come up and replace, basically swap places with the positive charge here. But if you look here, I don't have a hydrogen here. There's no way it's possible for me to write a hydrogen here because this carbon's already bonded to 4 things. So in this case, I can't do a hydride shift here, and I can't. It can't actually form a hydride shift here. However, you can do something called a methyl shift, right? So you can actually shift a full methyl. So this methyl guy here can actually shift towards here and form a methyl shift. So it would actually create a stable carbocation, right? So let me show you. I might have to show you a diagram as to how it works here. And I don't actually have that much time here. So let's see. It's basically this concept of carbocation rearrangements that these guys are trying to help you understand here. So let me think about this problem here. Yeah. So basically, you have again this. I kind of drew this poorly here. But again, I have this here is, you can think of it as a tertiary carbon, right? It's bonded to 4 different things here. So I'm not going to have like a hydrogen here. You can think of a hydrogen here, but why would I move my carbocation to a primary carbocation here? Remember, this here is already a secondary carbocation, right? So this here is already a secondary one. If it moves to a first one here, it's actually higher in energy level. So I want it to actually move down to a third tertiary carbocation. And the only way I can do that is if one of my methyls here do a methyl shift, and I push this away, right? So I push this, I basically bring this up, and then I get something. I'm gonna write here a methyl shift. Methyl shift. And then I guess this guy here was a hydride shift here. And this is just basically the reason why we do this is because we want to stabilize this carbocation, right? We have a secondary one, it can become a tertiary carbocation. So that I have now this methyl is going to stick up like that, and then have one, and then one. I simply have one here, and then my positive charge like so, right? So now, again, this here is a tertiary carbocation. It's much more stable than a secondary carbocation. Tertiary carbocation. Then what it's going to do is I still have my my H2O here, right? So with my H2O here, what I can do is it's going to bond to this oxygen here, right? HO here, minus here is going to bond to this guy here, and I'm going to get something like this. So this solution here, they said it's bonded to actually to the bromine here, and that is a possible kind of kind of solution here. So if I had a chlorine here, and if it didn't do a methyl shift here, if I said it didn't do a methyl shift, then I could say that if H2O here bonded, again, I have H2O here. This simply just attacked this guy here, and I didn't get a methyl shift. Then I would get my my products here, right? I would get the product, the solution that I would get on the left hand side here. So it depends on if the methyl shift occurs. In this case, it does occur actually. So this number 2 question, the solution here is actually wrong because of this methyl shift. The fact that I can one of these methyls can move up to stabilize the carbocation here to make it a tertiary carbocation. So in this case here, I'm going to say this number 2 is incorrect here, but I would have to look at number 3 and 4 here. So let me just write down. And only have 2 more minutes left, so let me just quickly check over the answers for you. I won't write this down here, but it says here I have some type of propane with a chlorine group plus bromine with DMF, and then I have 1, 2, 3 chlorine with iodine 2 and DMF as well. So again, these two are exactly the same chemical structures, but I'm adding different halogens with DMF here. And as you can see, DMF, again, is a very, very potent reagent, and what it does is it actually ignores this concept of electronegativity because of DMF, because it's a aprotic solvent. What it's going to do is, we know that Cl here is above bromine and iodine, so if you only have HBr or HI here, it's not going to kick out this chlorine, right? The electronegativity difference between chlorine and carbon is much higher than the electronegativity difference between carbon and bromine, or even carbon and iodine here. However, with the existence of this DMF, with this DMF solvent, what I can do is, remember, this is dimethyl formaldehyde, formad. I don't know how to pronounce that. I just call it DMF. But with DMF here, what it's going to do is going to create an acid-2 reaction, right? So it's actually going to be able to come and kick out this chlorine here. So basically, the reaction mechanism here, what's happening here, is that this chlorine here is going to leave. It's going to stabilize first with the DMF. It's going to create a resonance structure. So you get something like this, and I'll draw this out quickly for you. DMF looks something like this. I have double bond O, bond N, CH3, CH3. And then what it can do is, again, I can create a resonance structure here and say that this is yours O minus, double bond N, bond CH3, bond CH3, and this here is a positive charge, right? So again, this chlorine here, once it leaves here, it can be very much stabilized by this nitrogen here. So that's why this here is going to come and create this, it's basically going to act as this O minus is going to act as a kind of nucleophile first to here, and then it's going to form, basically bond with, kick out this chlorine here. So I would get Cl minus here, and then finally bromine then can come. This is a very, very good leaving group. Again, it's very, very big. It's not as stable here. Bromine can kick it out and make it a good leaving group. So this here is this here would be a correct solution. So I'm just going to write here, solutions are correct except the second question. There is a methyl shift to form a tertiary carbocation. So the hydroxyl group is attached to, what carbon is this? This here is 1, 2, 3 to carbon 3 instead of carbon 2. So I'm going to say solution here is incorrect, just because of that second question here. So that's going to conclude my video. I'm going to start off my second video with this problem here, and you can kind of tune in for that in about an hour. So again, thank you so much for watching. If you like the YouTube channel, definitely like, subscribe, and keep your notifications on for me to kind of stream. If you like my streaming, thank you so much. And yeah, again, thank you so much for watching. Stay safe, stay healthy, and have a great day. Take care.